I welcome you all to the session of engine system and performance, and the topics of our today's discussion are fuel control modes and then integrated engine control system. So, what we have learned from our previous classes is the need of an electronic fuel control system, and essentially this electronic fuel control system is needed to allow for an engine to operate with fuel economy and also to reduce emission level. And we know that an engine can operate under varied conditions, and if we need to have better fuel economy together with reduced emission, certainly that particular control system or control unit should be capable of performing some task to provide adequate or desired level of air fuel mixture for varied conditions. So, you know that control system, to be precise, engine control system is responsible for controlling the quantity of fuel across all or rather all operating conditions of the engine. So, as I said you that engine can run starting from idling to cruising zone and then power zone, that we have studied in our internal combustion engine course, idling zone, cruising zone and power zone. So, you know that if we need to have or if we need to ensure that the engine will run with optimum level always or design condition always, then it should be ensured that fuel air mixture to be supplied to the engine should be optimum or stoichiometric ratio always. And to do that, several functionalities are required. So, since the purpose of the engine control system is to control the quantity of fuel to be supplied to engine for all operating conditions, and issue is that there are a number of distinct categories of engine operation, and each of these operations, I mean there are number of distinct categories of engine operation, and each operation corresponds to a particular mode in the control system. So, if we try to write here that engine operation right. So, we have several and distinct categories, and each category corresponds to a specific and distinct mode, rather I should say operating mode for the engine control system. So, this is what is we can see, and so as I said that engine control system which is engine control system. This system is responsible for controlling the quantity of fuel to be supplied to the engine cylinder for all possible fuel quantity for all possible operating condition. So, this is very important. So, this is the task of the engine control system, and we had seen that an engine can operate under several and distinct modes of operation or several modes. So, an engine can operate under or an engine can operate following several modes, and each mode or each category corresponds to a specific and distinctive mode. So, that means, if we try to write in the next slide that we have engine mode, say for example, A, B, C, D, E, F like this. So, all these are distinctive categories. So, these are several categories of engine operation. Maybe idling, engine needs to accelerate, engine needs to decelerate, engine need to run in a power zone, engine is running in idling condition. So, all these possible categories are here. We really do not know how many such categories are there, we will see soon, and then each category corresponds to distinct and several modes. So, this is M1, this is M2, this is M3, this is M4, this is M5 and finally M6. So, try to understand, since there are a number of distinct categories of engine operation and each of them corresponds to a distinct mode of the for the control system, because why it is so? Because the difference between two operations, between A and B or B and C, or difference among all the operation is so large that it is not possible for any particular mode to control fuel for the categories of operation that we have discussed, right. So, the difference between two different categories of operation or difference among all the categories of operation is so large that a particular one or two different modes is not enough to control the fuel for all the categories of operation. And that is why each mode or each operation category need a particular mode, and all of these modes has separate software routine, right. So, basically it has software routine S1, it will be having S2, it will be having S3, this mode will be having S4, this is having S5 and this is having S6, right. So, difference between these two modes are so large that we need this dedicated software routine, for each mode, right, because difference between two categories of engine operation or among all the categories is so large that it is not possible for any particular mode to control fuel for all the categories of operation. Okay, so, this is what it is. Now, question is, having said this, that an engine needs say dedicated software routine for all the modes. So, now question is, that means if a particular engine has to switch between two categories of operation, say for example, when we start engine and then again when we try to draw up more power from the engine. So, these two are two different categories of operation. Maybe when we start engine, we can keep the engine just starting it for a few minutes, and then again we start engine or we try to draw more power from the engine. So, starting the engine will be having a particular category of operation, and then again when engine will try to produce power. So, that would be another category of operation. So, these two different categories should be controlled by two different modes, but essentially the engine control unit, that is the central part, should be able to supply required or required quantity of air fuel mixture or fuel to be precise for all the modes, even though the engine is shifting between or switching between one mode to another mode. So, that is very important. Now, then question is the control system. So, if we write here, the control system will house all these software routine essentially to control all these modes, which in turn will control all these categories of operation, right. So, the control system will house all these software routine, and as I said you, if the engine has to switch between mode 1 to mode 3 or from mode 1 to mode 2, that is M1 to M2, because maybe engine operation has changed from operation A category to operation B category, then the control system would be adjust or control system would be able to give some input to the injector to supply adequate amount of fuel that is needed as the engine operation is changing from category A to category B, and accordingly mode has to change, mode of operation has to be changed. So, this control system basically should determine the operating modes first, operating mode from the existing sensor data and call the particular software routine. Right, software routine to adjust to the changed condition, right. So, basically this is how the control. So, this is the central part. So, the control system will be having that particular feature. So, it should be able to determine. So, control system should determine the operating mode first from the existing sensor data, because there are many sensors, and determining the mode based on the measurement from existing sensor, then control system will call upon a particular software routine to change with the to adjust the air fuel ratio to the changed condition. So, that is how this works. Now, for a typical engine, typical engine there are 7 different engine operating modes. And these modes are, number 1 is engine crank or engine cranking, then number 2 is engine warm up, number 3 is open loop control that we have already discussed, number 4 is closed loop control. That means, we may require to switch the control system, we will call upon the software routine to change the mode to adjust to this changed operating condition, maybe from cranking to warm up, then warm up to open loop to closed loop. We will discuss this taking an example today. Then 5 is engine acceleration, right, or it is known as hard acceleration. Hard acceleration or heavy load. This is also heavy load. 6 is deceleration, okay. 6 is deceleration. Low load, and 7 is the ideal mode, okay. So, all these 7 distinctive modes of or engine operating modes are identified for a typical engine. So, we shall take an example to check how a particular control system or how a control system which is integrated to the electronic control unit of the engine is able to provide some control logic mode to change the operation engine operation from 1 to 2, then 2 to 3, 3 to 4 or 4 to 5 depending upon the requirement. Okay. So, it may so happen that from the warm up we may need to go for 5. So, certainly if we need to go from warm up to hard acceleration or heavy load, we need to go through this open loop, closed loop, etc., etc. But even if we do not require to go from open loop to closed loop or from warm up to hard acceleration or heavy load, certainly we had to cover these 2 different modes, but it is suddenly. So, the control system would be able or would be capable to perform some task, so that software routine, the control system will call upon software routine to adjust to the change condition, even if it is momentarily needed to change the operation from warm up to heavy load condition. So, let us now take an example. So, if we go to the next slide, I will be writing one line, then it will help you to understand the program for mode control logic. So, the program for mode control logic determines the engine operating mode, engine operating condition or category or mode, right, from the sensor data. Right. and timers. Right. So, essentially the control system, that is the central part of the electronic control system, is reliant on the sensors taking some feedback from the input sensors. The control unit of the electronic control system, the inbuilt program that is there is used to change the mode control logic, or to this mode control logic or control mode logic, or I can write or control mode logic. So, this control mode logic will swing between, or will determine. So, the program will first determine for the logic to be shifted from one mode to another mode. So, this mode control logic pass the control system from one mode to another mode, determining or estimating the engine operating condition at any particular instant of time using sensor data. So, that is very important. So, now let us, what it is very important, this is important to know, this is the basically method, this is the very important point based on which a control system works. So, if we now take an example, say an example we are taking now, an engine say E. So, this engine E I am writing first, then I will explain. If the engine, so number 1, when the ignition key is on, switched on. So, if we go back to the previous slide, I have written engine cranking. What does it mean? This engine cranking, let me write here, otherwise it would be again difficult. So, engine cranking is a process of using a starter to rotate IC engine so that it can start. So, that is very important. So, starter essentially, right. So, this is essentially why I am writing now, because although I had mentioned engine cranking, cranking refers to a process using a process of engine crank is a process of using a starter, is a process by using a starter to rotate the engine so that it can start initially. That means that even if you have two wheelers, we can have now battery operated system. If you switch on, the engine will start. So, that is the starter, engine cranking, we are starting the engine. So, now the example that we are going to discuss today, when the ignition key is on. So, essentially if you switch on the if you on the switch in your two wheeler, you are essentially turning on the ignition key. So, when the ignition key is on, the mode control logic on the mode control logic, that is MCL. I will be using the word MCL henceforth, because I need to write this 3 words frequently henceforth. So, when the ignition key is on, the mode control logic, that means we have start the engine, the mode control logic selects automatically selects an engine start control scheme, and engine start scheme, start control scheme, okay, start control scheme. So, this is I am again marking in this box in a scheme that provides high fuel, that provides high air fuel ratio, right, high fuel air ratio, I should write fuel air ratio, not the air fuel ratio, during engine start. So, this is the ideal zone. So, when we start the engine, we have studied from our IC engine course that we need to supply rich air fuel ratio, and that information should be given by the mode control logic. So, essentially the mode control logic of the control system automatically will select a particular mode. If we go back to the previous slide, so this software, those are software routine, the control system will use sensor to detect whether engine is now going to start or not. If the engine is, if we switch on the ignition key, engine will be, that means we are trying to start the engine. Software routine will allow mode control logic or MCL to select a particular mode of operation, and that mode is essentially, the mode should map to the scheme, and that scheme should be able to supply rich fuel air ratio, so that the to meet the requirement during that particular condition, right. Okay. So, if we go to the next, then number 2. So, now it is start, then if we so when engine RPM increases or rises above the cranking value, that means we started engine E, then initially we had to supply rich air fuel mixture which is required during that particular mode of operation or category of operation. Then when engine RPMs rises, essentially we are trying to extract more load from the engine. Now it will if it is a say 4-wheeler or 2-wheelers, so when engine will start, driver will drive the engine. So, then essentially drive engine needs to produce more power, then RPM will increase above the cranking value. Then what will happen, then controller, the control system essentially we can write controller identifies engine started. So, then control will identify that engine is already started and passes the control to program and passes mode control logic, to the engine warm up mode. Okay. So, that way, so that means try to understand, I have taken this example. When we start the engine, the requirement is to supply rich fuel air ratio, and that should be controlled by the controller or control system. So, essentially controller or control system will take or determine the condition from the input sensor data, then the software routine that is already mapped, already built in with the system, that software routine will be used, and mode control logic or MCL will allow or will select automatically a particular mode. So, mode controller logic has to map or will map a particular mode of operation or particular mode which should be compatible with the operating condition or operating category at that particular condition, right. So, when engine RPM will increase, that is what I told you few minutes back, that when engine needs to produce more power, that mode controller logic or control system will understand or will identify engine started. So, I have written within inverted comma. So, controller will identify the engine started again based on the sensor data, and then that controller will allow mode controller logic or will pass mode controller logic to the engine warm up mode. So, again we need to warm up the engine, that means we need to increase the coolant temperature. Okay. So, that this way this control system is responsible. So, essentially in this condition the air fuel ratio to be supplied to, if we write here, okay, and this operating mode keeps. So, these operating modes not modes, this operating mode keeps this operating mode keeps the air fuel ratio, low. Okay. Why it is? So, this particular, so essentially the controller will now pass MCL to the engine warm up mode, that is true, and essentially the sole objective is to again control the air fuel ratio, and that should be low. Why it should be low? If we go to the next slide. So, in the warm up mode, air fuel ratio should be low to prevent engine stalling or engine stall. Either during cool weather or cool weather until the engine coolant temperature rises above some minimum value. Okay. So, that means in the warm up mode we are trying to warm up the engine, and that is why if we supply more air fuel ratio beyond this stoichiometric one, then the presence of excess air in the air fuel ratio will take away certain amount of heat. So, instead of warm up, we will not be it will not be possible to increase the temperature of the coolant. So, it will stall. So, engine will stall. I have written the engine stall. So, if I mark here engine stall. So, engine stall means stalling of engine or engine stalling. Since I have used this word, I am writing the meaning of this word in this context. Engine stalling means engine when engine will stop while driving or idling. So, engine stalling means either engine will stop when engine will stop when engine is driving, or even engine can stop during idling. So, this is very important. So, essentially to prevent engine stall during cool weather until the coolant temperature reaches maximum, because we need to warm up. So, that is why air fuel ratio should be maintained low. So, this all these information should be provided by the controller or control system to the engine, to the injector species through several modes of control logic, or through several operational modes. So, you can understand how this system, that is control system, is capable to provide adequate air fuel ratio or fuel air ratio based on the need of the engine at a particular operating condition. Okay. Next, let us take this example for one case, then I will quickly complete it. So, say for example, hard acceleration, or as I wrote, heavy load. So, that means when we know from our understanding that if engine needs to produce more power, certainly to meet the requirement of heavy load, that means that is called hard acceleration. Okay. In that case, what we have understood from our internal combustion engine course is that rich air fuel mixture should be given to the engine. So, this is called fuel enrichment. Okay. So, which needs fuel enrichment. So, that means what will happen. So, if the engine from the cruising zone to change the operating mode to power zone suddenly, then again that sudden change in operating mode, operating condition should be taken care by the control system, so that engine stalling will not be there. If engine needs to produce more power, despite knowing the requirement of rich fuel air mixture, if the controller fails to supply that information to the injector, then engine will stall, right. So, this what happens here, the just I am writing for the sake of completeness, that the mode control logic MCL. So, this is mode control logic MCL. Okay. MCL chooses a scheme, right, that provides rich air fuel mixture for the duration of acceleration or heavy load, right. So, if we go back to the previous slide, so controller or control system will now receive some or determine data from the input sensors, and then that mode control logic or MCL will map a particular mode which will corresponds to that particular operation. So, if the operation changes from cruising zone to power zone, or cruising zone to the zone where we need heavy load or acceleration, then certainly mode has to map to that particular operational category. So, that should be given, that information should be given by the controller to change the mode control logic or to shift the mode control logic from one particular mode to another mode, and that particular mode will be compatible with the particular operating condition, and accordingly air fuel ratio would be supplied, because all these modes are responsible to supply air. So, say for example, mode 2 is responsible for supplying rich air fuel mixture. So, essentially controller will allow mode control logic to shift to M2, so that M2 is now M2 corresponds to operating condition B, that means heavy load condition. That way it would be adjusted. Now, the question is, okay, now the question is, if the so what happens, maybe in this zone if we supply rich air fuel mixture, certainly maximum torque will be produced, but it is not possible to have fuel economy and better emission. So, though in this regime torque produced will be maximum, with a compromised fuel economy and emission, right. So, so as compared to stoichiometric one, to some extent, though we are trying to have maximum torque, so we have to compromise the fuel economy, because it should be little away from the stoichiometric air fuel ratio, and essentially emissions should be beyond control. So, I mean we have to compromise. Now, the question is, if the need for enrichment is over, so when the need for enrichment is over, right, control or mode control logic is returned either to open control or closed control. Closed control depending on the, so I should write control is returned either to open control or closed control depending on the selection of mode control logic, depending on the control mode logic selection condition, that selection of MCL at that condition. So, if the requirement of that heavy load requirement is over, so now engine will face or encounter another condition. So, at that particular condition the control has to return either to open control or closed control depending on the selection mode control logic. So, controller will allow mode control logic to again map either with M1 mode or M2 mode or M3 mode depending on the state of the condition. So, if that particular period is over. So, this way the control system works, and essentially you can understand the sole responsible is to control the amount or quantity of fuel to be supplied to the engine. Okay. So, now what we can write, if we summarize this control system, then we can write. So, the control system selects an operating mode based on the instantaneous operating condition comma determined from the sensor measurements. This is number 1. This is number 1. Number 2 is within any given operating mode. The desired air fuel mixture is selected, that is very important, and this is desired, this is not stoichiometric, and that is what we had seen. Even engine needs to the engine requires stoichiometric air fuel ratio during cruising zone, controller will supply. If engine experiences heavy load or acceleration, certainly the stoichiometric air fuel ratio should be deviated. So, air fuel ratio should be deviated from the stoichiometric one, and engine needs rich air fuel ratio. In that condition, we had seen few minutes back that maybe engine will produce maximum torque essentially to produce heavy load, but with a compromised fuel economy, and if the fuel economy is not there, certainly emission level cannot be controlled. So, air fuel mixture is selected, okay, and the controller then determines the quantity of fuel to be injected into each cylinder during each cycle. So, the quantity of fuel is dependent on the particular condition the engine will experience. Okay. So, this is all about the control modes for fuel control. Now, let us briefly discuss about integrated engine control system. So, what is integrated engine control system? You know that with the advent of digital technology, of course, sensor and other electronic devices, electronic gadgets, with the advent of digital technology, it is possible to integrate various function into an integrated circuit, right. So, so we can see that from our previous discussion that a typical engine is having 7 different operating modes, operating conditions, and the difference between 2 operating conditions or among the operating conditions is so large that it is not possible to have any particular mode to control or to provide desired air fuel ratio into the engine cylinder. So, what we had discussed that we need to have separate software routine for 7 different operating conditions or 7 different modes. Now, question is with the help of with the advancement of digital technology, it is possible to integrate various functions into a single control unit. So, essentially the control unit, that is the central unit, that is the controller. So, that should be a single unit. It is not possible to have 8 or 7 different control units to control 7 different modes. So, if we go back to the previous slide, you can see that here what you can see that there are several engine operation categories, and to control all these categories there are several modes, right, of or several control modes, but all these control modes should be controlled by a single unit instead of 7 different units, and that is possible with the advancement of digital technology. Not only with the advancement of digital technology, with the advancement of digital technology, computer algorithm and softwares. So, these three advancements or developments have led to integrate several functions into a single unit, and that is what is integrated control system. So, if you go to the next slide, integrated control system, that as I said you that it means the control system or control systems, the control system are integrated into a single unit, and this is possible with because of the advancement of, I am writing, digital technology, computer or computational algorithms and software. Okay. So, in earlier engine in many cases had several control units or control systems, but the trend at present is to have a single unit, because that is possible using all these advancement in the field. Now, the question is, if we can have an integrated control system. So, the integrated control system is having certainly distinctive advantage and disadvantage. The disadvantage is it is more compact, and so many electronic gadgets, so many electronic circuits are placed therein, and we need to have efficient cooling, or so that that particular unit can run smoothly without encountering any problematic issues. So, the cooling should be there, and that is also known as MEMS cooling. So, integrated control system is compact and several electronic circuits are placed therein. So, cooling is an issue. If adequate or proper cooling is not, or arrangement is not made, then that particular system may fail. But the advantage is this particular this integrated control system ICS or systems has the capability to maintain stoichiometry and simultaneously optimize ignition timing, right. Ignition timing and fuel control, or control over ignition time and fuel injection period, these two are the very important things if we can have proper ignition and if we can have proper air fuel ratio to be injected or to be drawn into the engine cylinder, to be injected into the engine cylinder, then combustion can be efficient and also emission can be reduced. So, integrated control system or systems, I should write here system, integrated control system has the capability to maintain, I have to maintain stoichiometry, that is closer to the stoichiometry. I mean, of course, if the requirement is heavy load or acceleration, certainly the air fuel ratio should be deviated from the stoichiometric air fuel ratio, otherwise it will be able to maintain stoichiometry in the air fuel ratio and simultaneously we will maintain optimum level of emission and also ignition timing. So, to summarize our today's discussion, we had discussed about control modes for fuel control, to be precise, because which is very important, and then we had discussed about integrated control system, and the present trend is towards the integrated control system. Instead of using multiple units, we can integrate several functions into a single unit. But we have also mentioned or discussed about the disadvantage of this particular system, that is integrated control system. Excessive heat generation needs adequate cooling. Otherwise, this particular system has advantageous feature of providing stoichiometry or closer to the stoichiometry and also optimum ignition timing. With this, I stop here today and we shall continue our discussion in the next class. Thank you.